Okay, we have a problem now that we need to analyze, and we're going to use all the expressions related with the annual equivalent value. The exercise we have in front of us is the corresponding problem of a person who has spent 1,000 at present and has a debt that has to be paid in 10 years due to an annuity A, assuming we have to charge a 7% rate of discount. What is more precise, a 7% rate of interest levied by the financial entity that pays for that finance the operation. Okay, for doing so, we have to establish this balance equation that we're going to build now. We have here an initial value of P equal to 1000, and this has to be equal to the sum of the first n terms of a series formed by the annuity, the contribution of each one of the terms of an annuity to the present value of this known annuity. Each one of the terms has a present value of 1 plus of a divided by 1 plus r up to n, up to t, corresponding to the moment this payment is made. Okay, so this is the equation we have to balance. Determine A so that the present value of the terms is equal to the known value of the 1000 present value that has been spent by the agent. Okay, how to develop this is pretty simple. We capture this expression. Oh, something is wrong here, so we have to repeat. Sum A okay. This expression can now be treated as a geometric progression with the formula we all know. The formula says that the sum of the n terms of a geometric progression is essentially the first term of the progression, that is again a fraction, 1 divided by 1 plus r, minus the last term of the progression times the rate of the progression, and the rate in this case is this term 1 over 1 plus r. So this is equivalent to frac over 1 over 1 plus r up to n times, again under fraction, the last term times 1 over 1 plus r. Okay, and this has to be divided by 1 minus the rate, that is again 1 over 1 plus r. Okay, if we now operate in this expression, we will see that at the lower part of the fraction, this expression is transformed into 1 plus r minus 1, that is r. Okay. And this. Okay, so r is the only remaining term, and we can now take out the 1 plus r in the in the fraction. Okay. What if we now take out this common term of 1 plus r in the upper part of the expression? We get this. Okay, and then what we have here is expression then 1 over 1 up to n. Okay, perfect. Now we have the expressions quite simplified, because we can also get rid of this expression. Okay, and this is equal to a times okay, we have r here, and here we have 1 plus r up to n minus 1, and the remaining term has to be taken here, 1 plus r up to n. Okay, and then this expression that can be easily computed with a calculator has to match the corresponding equation condition. Okay, perfect. So now we can operate with this model we have already developed. We're going to do it in different ways, just to present you how to handle the issue. the issue. Then we open Maxima here, version. Then we load package ingecon as suggested. Okay, this expression will act differently depending on how your installation is made, obviously. And then first we will establish the condition. We want to solve the expression a times, and we open here brackets for the upper part of this of the fraction, 1 plus r up to n. Okay, sorry, first we will give values, numerical value to resolve. We will use Ri for the rate of interest, that is 0.07. Okay, then we will determine that n number of periods is equal to 10. Okay, so now is the moment when we can handle the issue. Oh. Sorry, some problems here. Okay, now we can solve the expression a times 1 plus r. I will use the numerical value up to np, okay, minus 1, I close bracket, divide by 1 plus ri up to n, divide again by ri. Then we have the left side of the equation is equal to 1000, and we have to solve for a, and we want the solution for numbers, numerical solution, not the the exact fractional result. We have this. Okay, we can close all this, and we have a value. Oh, so something is wrong here. I didn't take into account that n is an unknown value, and is np the number of periods. Okay, so the annuity that matches this equation is 142. Okay, now we're gonna demonstrate that how the formulas serve the same purpose as we have done. we have an expression that says that the present value of an annuity whose value is, or the present value 1000, the rate of interest is Ri, and the number of periods is this one, 10 in this case. Okay. So the annuity of present value of 1000 is 142 again, as has been expressed. I will tidy up this. Okay. So we have the expression here. Okay. Now let's have a look how this expression, how this result, how this annuity is variated when the rate of interest is moved. For this purpose, we will plot the equation that is known here, A over B of 1000, let's keep 1000 valid, R will be kept as a variable, and NP will be maintained. This expression will be plotted for a rank of R between 0 and let's say 25%. Okay. Okay. We want the grid to be plotted. X label will be maybe discount rate. E label will be annuity dollars per year. And title will be annuity equivalent everything is here. And we can observe this now. Just to be sure that the scale is okay, I will add an additional condition, that is the vertical axis will move from 0 to 300. Okay, doing so, we'll see how the initial value of the annuity without any kind of discount rate, that means without any financial charge, will represent a 10, sorry, will represent a 10 payments of 100, what is pretty straightforward. And then if we introduce a rate of interest, it will charge additional costs into the process. The value is increased. For example, in order to make an increase in the annuity of 50%, that means jumping from 100 to 150, we need some rate of discount. Should be determined, but this probably around 6.5, something like that, according to the scale. And If we just move up to 15% rate of discount, more than double of the 6.5 we have estimated, we then have double the annuity from jumping from 100 to 200 and so on. So this way we have transformed one initial payment of 1,000 into 10 payments of 200. Any change in the analysis will produce more or less the same equivalence. So if we just want to add an additional payment, let's move this, let's capture this, let's analyze how the initial payment of 100 is transformed into, let's introduce Ri in this case, and let's use n as an initial payment, and then let's think of n, number of periods that can move from one payment to 20 payments, an annuity of one single period or 20. Okay, now the X label will not be discount rate by number of periods for the R equal 7%. Okay, and let's keep this aside for a moment. Sorry, n is a new horizontal variable. If we move that way, we'll observe that one payment of more than 1,000 will be necessary to pay with 1 year delay, and each time we add additional payments, we reduce the annuity, although we pay with a given amount of money dedicated to pay the financial cost of the operation. As short as the annuity is, less financial payments we made and more reimbursement. And if we move to the future, we will observe that there is no much differences between paying 16, 18, or 20 payments. Okay, actually we pay with the same amount of money per year. The annuity is something around 100, and what we're increasing there is the total amount of financial cost of the process. Okay, that's all for the moment.